Hello everyone, this is our video example, the second video example for our multiple reactions. So there's a corresponding lecture that we talked about, how do we solve a multiple reaction problem. This is question 4.69 from the textbook, page 201. So flip open your textbook, read the question and follow along as we go through this problem right here. All right, in this question, it's given that ethanol can be produced by the hydration of ethylene. We're given the chemical reaction right there. Some of the product is converted to diethyl ether in a side reaction that we don't want. We are told that the feed to the reactor contains ethylene, steam, and an inert gas. When we analyze the effluent gas that comes out of the reactor, we are told that we know the mole fractions of the components that are coming out of the reactor. And so we are supposed to, in part A, take a basis of 100 moles of effluent gas, draw and label the flow chart, and then do a degree of freedom using atomic species. Again, I'm going to do a degree of freedom using all three methods because we want to make sure that we can do all three methods and show that they are consistent. All right, so let's go back to the problem and draw a process flow diagram. We are still in a single unit process, so that's simple enough. We just have a single reactor, and we have an input stream and an output stream. So in this case, it's still the same. I am going to write our equations or our chemical reaction equations at the top. So we have C2H4 plus H2O to give us our ethanol. And then we have an unwanted side reaction where the ethanol that is produced goes into a product that we do not want in this side reaction down here. So again, this is reaction 1, this is reaction 2. Okay, so we have our two reactions going on in this reactor. We have a feed. The next line says that the feed to a reactor contains ethylene, steam, and an inert gas. And we do not know anything about the compositions or the amounts. So we're going to go ahead and just label these as unknowns over here. We have ethylene, that's an unknown in the feed. We have steam, so water as an unknown, and then we have an inert that's an unknown down here. So we have our three unknowns in the feed. Now we are given that the compositions of our effluent stream. So we know that down here in terms of the mole fraction, we have ethylene is 43.3%. We are told that 2.5% of our ethanol, so that's what we want. We are given 0.14% of the ether. And then we are also given 9.3% of inerts. And the remaining is water. So we know that everything else that is not part of here is water, which means this is just essentially the 1 minus the sum of all the y's that are up here. And once you put it into the calculator, you see that this is 44.76. So 0.4476. Okay, and we are told to take a basis of 100 moles of the effluent gas. So we know a basis of N1 is equals to 100 moles, and that's our basis. All right, that's our fully labeled diagram that we have. Everything that we need to have is accounted for in this diagram. And in this case, we actually only have three unknowns, which is all on the feed side. So it seems to be simple enough where we only need to solve for three unknowns. All right, so the question calls to do our degree of freedom using the atomic species method, but I'm going to start doing the molecular species first. And then after that, we're going to go on to the atomic species to make sure that we can get it consistent. So we have our molecular species, DOF. So the first thing is we have our three unknowns. Next thing we need to do is to add our two reactions. So in this case, we have two reactions. And now we need to look for the number of species. In this case, we have all the species down here. We have 5 different species. So we have C2H4, we have H2O, we have our inert, and then we have our two products. So we have 3 plus 2 minus 5. That's all the information that we have, and we have 0 right here. All right, so in this case, based on the molecular species degree of freedom is telling us that we can solve this problem given the information that we have. I'm not going to go through the extent of reaction degree of freedom because all we're going to do for the extent of reaction equation is essentially take this one and split it out. We're going to call these 4 as our reactive species and then this as our non-reactive species. Essentially everything else is the same. We're just splitting these molecular species into 5 different ones for the extent of reaction. So I'm not going to go through that, but let's go through the atomic species degree of freedom. Now let's look at the atomic species degree of freedom. Same thing, we only have 3 unknowns. Nice thing about atomic species is we do not add additional unknowns for reactions. Next thing we do is we are going to count the number of reactive atomic species. In this case, we have carbon, hydrogen, and oxygen. So 3 reactive atomic species. And we have a non-reactive molecular species, 1 inert. And suddenly you realize we have a weird degree of freedom here, which gives us a -1. That's number 1, inconsistent with our molecular species degree of freedom. And number 2, typically when you see a negative degree of freedom, you are talking about a system that's overspecified. So you have some inconsistencies going on in this system. So what is going on down here? It turns out that in terms of atomic degree of freedom, this is usually the one that will give problems because the balances are not as obvious. We talked about this idea of independent balances before, and it turns out that these 3 species balances, and it's not obvious in terms of how they are related, but these are not independent. All 3 of these are not independent. It turns out that if you try to solve these 3 simultaneously, you will not be able to solve for 3 unknowns. They are essentially, one can be written as a linear combination of the other. It is not obvious, again, it's not obvious how we can do that, but just based on the degree of freedom that we see here, this is telling us that out of these 3, we can only use 2 of them. So these are non-independent, which means we can only use 2 of them. And in this case, it turns out that you can either use C and H, C and O, or H and O. You just can't use all 3 of them, and we do not need all 3 of them. We only need 2 of the balances and then 1 inert, 1 non-reactive species, molecular species balance, and we can solve this problem for our 3 unknowns. All right, so now let's go ahead and try to solve this problem. So I'm going to solve this problem using an atomic species method. I'm not going to go through the extent of reaction. I will post the solutions online with the step-by-step showing all the calculations for the extent for reaction as well. So if you want to try that method to get the same answers, you can go ahead and do that and then just look up the solutions. But what I'm going to do is the atomic species method, and just a recap of what we did. We have 3 unknowns here. We saw that we can only use 2 of the species balances, either C or H or O, and out of these 3, we're going to pick 2 of them. Any 2 of them will work, and then we have an inert balance. So let's start with the easy one. Let's start with the inert balance. Inert balance is simply, because it's non-reactive, we know 0 equals to in minus out. And what's coming in is right here, is in our NIF. What is coming out is 0.093 multiplied by 100. That is the number of moles of inert that's coming out. And so in this case, we can figure out our moles of inert right here of 9.3 moles. All right, so that's the first one that we need to do. All we are left with are our atomic species balances, carbon, hydrogen, oxygen. I am going to use my carbon and my oxygen. You can again use carbon and hydrogen, hydrogen and oxygen. Go ahead and try that. You should be able to get the same answer down here. So I'm going to do my carbon balance. So in terms of my carbon balance, remember for atomic, it's always just in minus out. You cannot generate or consume atoms. Carbon is coming in C2H4. And for every mole of C2H4 that I have, based on the chemical formula, I have 2 moles of carbon. So I have a 2 right in front here. Carbon is coming out in my C2H4 here. So this is the number of moles of C2H4 that's coming out in stream 1. And again, it's for every mole of C2H4, I have 2 moles of carbon. It is coming out in my ethanol, and same thing, it is 2 moles per mole of ethanol. So I have 2, 0.025, and 100. We have it coming out in this ether. So in this case, we have, I'm going to continue down here. For every mole of ether, I have 4 moles of carbon. And that's all we have for our carbon balance. So you can see if in this case, if we solve this, we can get our number of moles of C2H4 in the feed. And if you put in the numbers and crunch it, you have 46.08 moles. All right, so we have one more to do. You can either use your hydrogen balance or your oxygen balance. The remaining unknown is our number of moles of water that's coming in. So again, the hydrogen or oxygen will be fine. In this case, I am going to do my oxygen balance. All right, so 0 equals to in minus out again. It's coming in water. And it's 1 mole of oxygen per mole of water. On here, it's coming out in my ethanol, my ether, and my water, but they're all with 1. So there's only 1 mole of oxygen per mole of each one of these molecules. And so I have, this is my ethanol. I have my ether, and then I have my water. And so in this case, this is the unknown that I have left in here. And so I can solve for my moles of water, put it into your calculator. We have 47.4 moles. So now that we have solved for all unknowns, we are not done. Remember to always go back to the question and see what needs to be answered. We have solved for these, so let's put it down here. We have 9.3 moles down here. In terms of the water, we have 47.4. And the amount of C2H4 in the feed is 46.08. All right, so what the question asks for, the first thing is the percent conversion of C2H4. The percent conversion, the definition of fractional conversion of C2H4 is how much has reacted over how much you put in. In terms of how much has reacted, it is what went in minus what went out divided by what went in. So in terms of symbols, this is the number of moles of C2H4 in the feed minus the number of moles of C2H4 coming out divided by the number of moles of C2H4 in the feed. So if we put these numbers in here, we have 46.08 minus 0.433 times 100 over 46.08. And that gives us 6.03%. So the fractional conversion of our C2H4 is 6.03%. All right, the next thing it asks for is the yield. The yield of our ethanol. The definition of yield is the amount of C2H5OH that we get over ideally how much we can get. So the amount of C2H5OH we are getting is what we get out of our product down here. And the question is, what is this ideal number of moles of C2H5OH that we can get? definition of this is we do not have this second side reaction, so none of the products that we get will go into the ether that we don't want, and we are assuming that all the C2H4 is going to get consumed in the reaction to form our C2H5OH, which means if we were to relate that to our reactant, this would be equals to the ideal number of moles is essentially the number of moles of C2H4 that we fed into the system, presuming or assuming that all of this is going to get reacted in reaction 1. Okay, so now we put this in. We have 0.025 times 100, that's the number of moles of ethanol that we got, and the number of moles of C2H4 we put in is 46.08. And so we get a yield of 0.054. So a relatively low yield of our ethanol. All right, the last one is selectivity. Selectivity is generally the easiest specification to understand. All selectivity is the ratio of your desired product over your undesired product. So our desired product is our ethanol in the product stream. Our undesired product is our ether in our product stream. And we already have those numbers, so we have 0.025 times 100 divided by 0.0014 times 100. You realize that we actually don't really even need to multiply by 100 down here. And we end up with 17.9. So we have a selectivity of 17.9. So you can go ahead and redo this entire problem using the extent of reaction method to solve for these three unknowns. You should end up with the same amounts down here, and you can go through this same process to get my fractional conversion, the yield, and the selectivity. Like I mentioned, the solutions is posted online, so I'm not going to show it down here. So this is all we have for this example on multiple reactions. In the next lecture, we're going to start to put everything together and look at multiple units. So we're not just having a standalone reactor anymore. We're going to have different other units. I'm going to make it into one giant complex problem, and we'll see how we can solve that. So work hard, be smart. I will see you in the next lecture.